In substitution reactions, one group is being replaced by another group. For example, in this reaction, X is replaced by Y. In substitution reactions, we need a substrate with a good leaving group. For example, we need an alkyl halide because halides are good leaving groups. And we need a nucleophile. And nucleophile will replace the leaving group of the substrate. For example, in this reaction, this is the substrate. It is an alkyl halide, and chlorine is the leaving group, and this is the nucleophile. So as you can see in the product, we have replaced the leaving group with the nucleophile. So chlorine is being replaced with SH. And this is a substitution reaction because one group, chlorine, is replaced with another group, SH. Possible mechanisms for substitution reactions are SN2 and SN1. In SN2 mechanism, rate of reaction depends on concentration of both substrate and nucleophile. In SN2, S stands for substitution, N for nucleophilic, and 2 for bimolecular, which means rate of reaction depends on concentration of two different compounds. In SN1 mechanism, rate of reaction only depends on concentration of substrate. In SN1, S stands for substitution, N for nucleophilic, and 1 for unimolecular, which means rate of reaction depends on concentration of only one compound. SN2 is a one-step process. Nucleophile attacks the substrate from the backside and leaving group leaves. Nucleophile attacks substrate means that a new bond starts to form between nucleophile, lone pair of nucleophile, and electrophilic center of the substrate. And we show this bond formation with this arrow number 1. The second arrow shows that bond between leaving group and substrate starts to break, and leaving group is taking both electrons of this sigma bond and leaves the molecule. SN1 is a stepwise process. In SN1 mechanism, first leaving group leaves the substrate. So this arrow means that bond between substrate and leaving group is breaking. So leaving group takes both electrons and leaves. Now a carbocation forms, and in the next step, nucleophile will attack the carbocation and product will form. In SN1 mechanism, carbocation formation is the slow step, and it is the rate determining step of SN1 reactions. This is the energy diagram for SN2 reaction. So here we have the reactants. At the end, we have the free energy of products, and energy maxima is free energy of transition state. The difference between free energy of transition state and reactant is activation energy. And this is the energy diagram for SN1 reaction with 2 steps. This is free energy of reactants. At the end, we have free energy of products. Here we have free energy of the intermediate, which is carbocation. And this reaction has 2 transition states. This is free energy of the first transition state and free energy of the second transition state. The first step, which is carbocation formation, has a larger activation energy, and it is the rate determining step of SN1 reaction. So rate determining step of SN1 reaction is the carbocation formation, the step that carbocation forms. All the other steps have lower activation energy. SN2 reaction is backside attack, which means that nucleophile attacks from the opposite side of leaving group. And the reason is that nucleophile and leaving group are both electron-rich groups. So nucleophile cannot get close to the molecule from this side, from the side that leaving group is. So it has to attack from the back side to the alpha carbon and kicks out the leaving group. This is called backside attack. In SN1 reaction, first the carbocation forms, and carbocations are planar. So here we have a carbocation. Hybridization of carbon with positive charge is sp2, so it is planar. And now nucleophile can attack from front or from back. Okay, so nucleophile can attack from either side. It can attack from front side, or it can attack from the back side. In this video clip, you can see the SN2 reaction between bromoethane and hydroxide. And product of reaction is ethanol and bromide. The red atom is oxygen in the animation. The red atom is oxygen, so this is OH. And then on the other side, you can see ethyl bromide or bromoethane. bromine is almost yellow. So it's CH3, CH2, Br, and it is reacting with hydroxide, OH. Hydroxide and bromine are both electron rich. So hydroxide cannot get close to alpha carbon from the front side where the bromine is because they repel each other. Hydroxide has to attack the alpha carbon from the back side, from the opposite side of bromine. And that's why we call SN2 reaction a backside attack. So as you can see, a sigma bond starts to form between oxygen, the red atom, and alpha carbon, and bond between alpha carbon and bromine, the yellow atom, starts to break, and a transition state forms. In transition state, as you can see, alpha carbon has 5 bonds, and pentavalent carbon is very unstable. And then bond between bromine and alpha carbon completely breaks, and bond between alpha carbon and oxygen completely forms. So here you can see the SN2 reaction again. Pentavalent carbon forms transition state, very unstable, and then leaving group completely leaves, and the final product forms. Now let's see what type of substrate is more reactive in SN2. Remember, we have metal substrates, a methyl group which is bonded to leaving group, primary substrates, that alpha carbon is primary, like this one. This is a primary substrate. Alpha carbon is bonded to one other carbon and 2 hydrogens. Substrates can be secondary, like this one. Alpha carbon is bonded to 2 other carbons and 1 hydrogen, and tertiary substrates, that alpha carbon is bonded to 3 other carbons. Okay, now in SN2 reaction, nucleophile has to attack the alpha carbon from the back side. And when we look at the alpha carbons in metal substrate, primary, secondary, and tertiary, we will see that alpha carbon of metal substrate is the least crowded one. So it's for nucleophile, it's very easy to reach the alpha carbon of metal substrate. Alpha carbon is bonded to 3 small hydrogens. In primary substrates, the alpha carbon is bonded to 1 alkyl group, 1 bulky group, for example, a CH3, and it has 2 hydrogens. So it is still easy for nucleophile to reach the alpha carbon of primary substrates. In secondary substrates, there are 2 bulky groups, 2 alkyl groups bonded to the alpha carbon. So it's harder for nucleophile to reach the alpha carbon of secondary substrate compared to alpha carbon of primary. And tertiary is the worst one because the alpha carbon is bonded to 3 alkyl groups. So it's very hard for nucleophile to reach the alpha carbon of a tertiary substrate. And these are the energy diagrams for SN2 reaction of metal, primary, secondary, and tertiary substrate with the nucleophile. As you can see, SN2 reaction of metal substrate has the lowest activation energy, and SN2 reaction of tertiary substrate has the highest activation energy. Okay, when you look at the transition states, you can see that transition state for tertiary substrate, this one is the least stable one because it has a pentavalent carbon and it's very crowded. So the repulsion between all these bulky groups makes the transition state of tertiary very unstable. And transition state of the methyl substrate, this one is the most stable one because the repulsion is between 5 bonds and 3 of them are small hydrogens. Then the repulsion between the groups increases in primary, it's more in secondary, and it's maximum in tertiary substrates. So we know that highest activation energy means the slowest reaction. So we can rank different substrates based on their reactivity in SN2 reaction. Methyl substrate is the most reactive one, and tertiary substrates are the least reactive one. Order of reactivity of substrates in SN2 reaction. Methyl substrates are the fastest, then primary, then secondary, and tertiary is the slowest one. In each pair, identify the compound that undergoes SN2 reaction faster. In the first one, we have a primary alkyl halide, primary substrate, because the alpha carbon is the carbon which is bonded to the leaving group. Alpha carbon is bonded to only one other carbon and two hydrogens. So this is a primary substrate. The second compound is a secondary substrate. Why? Because alpha carbon, the carbon which is bonded to the leaving group, is bonded to two other carbons, two alkyl groups, and one hydrogen. So this is a secondary substrate. We know that in SN2 reaction, this is the order of reactivity of substrates: methyl, primary, secondary, and tertiary. So primary substrates react faster in SN2 reactions, which means this one reacts faster in SN2 reaction. In B, the first compound, this is the alpha carbon, and this is a primary substrate. Why? Because the alpha carbon is bonded to only one other carbon, one alkyl group, and two hydrogens. So this is a primary substrate. The second compound is secondary because alpha carbon is bonded to two other carbons and one hydrogen. Again, primary substrates undergo SN2 reaction faster, which means this one undergoes SN2 faster. In C, the first compound is a secondary substrate because alpha carbon is bonded to two other carbons, two alkyl groups, and a hydrogen. The second compound is tertiary because alpha carbon, this carbon is bonded to one, two, and three other carbons. Alpha carbon is bonded to three alkyl groups. And again, we know that secondary substrates undergo SN2 reaction faster than tertiary, which means this one undergoes SN2 reaction faster. Now let's check a stereochemistry of SN2. Experiment shows that when alpha carbon is chiral and undergoes SN2 reaction, in general, configuration of the alpha carbon will change. For example, if configuration of alpha carbon before the SN2 reaction is S, after the SN2 reaction, in general, it becomes R. And it is said that SN2 reaction proceeds with inversion of configuration. R becomes S, S becomes R usually. And this inversion of configuration in SN2 reactions is another evidence that confirms the backside attack in SN2 reactions. Look at this reaction. Sulfur will attack from the backside. This is the alpha carbon. So sulfur will attack from the backside and kicks out bromine. Substrate before the reaction, configuration of alpha carbon is S, and after the SN2 reaction product, configuration of alpha carbon is R. Here you can see the mechanism of reaction. So sulfur will attack the alpha carbon, and bond between alpha carbon and bromine starts to break, and this is the transition state. Bond between alpha carbon and sulfur is in the process of formation, and bond bond between alpha carbon and bromine is in the process of breaking. And finally, bond between alpha carbon and bromine completely breaks. Bond between alpha carbon and sulfur completely forms. And this is the product. Configuration of alpha carbon in the product is R. So the reaction proceeds with inversion of configuration. And the reason for this inversion of configuration is that SN2 is a backside attack. So it will change the configuration of the chiral center. Effect of leaving group on SN2 reaction. The better leaving group makes the SN2 reaction faster. For example, here we have two primary substrates because the alpha carbon is bonded to only one other carbon and two hydrogens. This is primary. Again, here the alpha carbon is only bonded to one other carbon and two hydrogens. When I say one other carbon, I mean one alkyl group. So they're both primary substrates. And if we use the same nucleophile, if they react with the same nucleophile, one of them will react faster than the other one. Which one? The one with a better leaving group. So here we have, in the first one, we have bromide. So when it leaves, it becomes bromine with a negative charge. And in the second compound, leaving group is iodide. If you check the periodic table, you will see that bromine and iodine are in the same column, in the same group. And iodine is larger than bromine, which means it can stabilize the negative charge better than bromine. So iodide is more stable, and it is a better leaving group. And this compound, the one with better leaving group, undergoes SN2 reaction faster.